All right, which color should we use? 1, 2, 3, 4, or 5? Number 5, we'll use purple. Here we go. All right, what we're going to do is determine the continuity. Let's turn that light down just a little bit. On the interval from -2 to 1. Notice that this one is open on one side and closed on the other, and we really need to be looking at these two definitions about continuity on an open interval versus closed interval. And I'm not going to graph a lot of these, but what I am going to do is just go ahead and figure out some of the continuity. And personal opinion, I like to go for the low-hanging fruit first. I'm going to go for this little guy. This function, cosine, is a wave, and it just goes up, down, up, down, up, and down. So this one is continuous for all of its domain, which is -infinity. So continuous on, let me put that word in the middle, on -infinity to infinity. So that's its domain. It never has a discontinuity on the entire thing because we just know what that graph looks like. So let's start back at the beginning. That one's the crazy one. We'll talk about that one in a minute. You're like, what's this double bracket thing? All right, so let's see. We are going to have, I'm going to switch colors for this. I'll talk about continuity in purple, and then we'll actually answer these questions. So let's see, we have x minus 1 divided by, we're just simplifying, x plus 2, x minus 1, which cancels those, and it gives me 1 over x plus 2. So we have a discontinuity at -2 for sure, and also we have a hole in the graph at +1. And I think it's worth noting, so we're going to have a vertical asymptote, I'll abbreviate it like this, at x equals -2. And we're also going to have a hole in the graph, and we can call that removable, because that's what it is. Removable, there we go. At x equals +1. Because there is a hole in the graph, if I wanted to redefine what the function is at that point, I could just easily assign it. I could plug a 1 in right here, and I would have 1 over 3, right? So, excuse me. Get choked up talking about holes in graphs. So this function has a discontinuity at x equals 1, but it's a removable discontinuity. And so the logical place of that hole, the place of that hole, is at +1 comma 1/3. All right, enough about that one. If this function is broken, so to speak, if this function has a discontinuity, it's going to happen at 1. And so if I plugged a 1 in here, I'd have 2 to the 1, so that's 2. If I plug a 1 in here, I'd have -1 plus 3, so that's 2. So this one is actually continuous on its entire domain, and that's from -infinity to infinity. And then we come to this that looks very similar, and same idea. If this function is broken, it's going to have potentially a jump discontinuity at x equals +1. And that's going to happen because we are dealing with one piece, 2 to the x. I'm going to graph this little guy real quickly, just jotting it down. -x plus 1 would be this line right here, and that applies less than 1, so there we go. And then the curve 2 to the x, of course, is exponential. If I plug in a 1, I get a 2, and it's going to go like this. So we're going to have a non-removable discontinuity, also known as a jump discontinuity in this context. We have a jump discontinuity there, and I could have just figured that out by saying, well, 2 to the 1 is 2. Plug in a 1 here, we'd have 0, and we see that. We see that because one of the y values is 2, the other y value, where the hole is, where the open circle is at 0, and so we have a jump discontinuity. So this one has a jump, also non-removable, discontinuity at x equals 1. Okay, and now we're going to get to this crazy guy right here, and this is going to take a separate piece of paper. I'm going to put it on a Post-it note just so it doesn't get mixed up with other things. This is called the greatest integer less than or equal to x. Like, what? All right, I'm going to try to squeeze these words in here. Greatest integer less than or equal to x. So what I'm going to do is give you a number, and you are going to take it down, round it down to the very next integer that's just below it. All right, so here goes. Let's make up some values. If I have some x value, and then we're going to have the greatest integer less than or equal to x. This is also known as the floor function. There's a ceiling function that rounds things up. Very appropriately named, huh? And there's the elevator function that just goes back and forth. I'm kidding, I made that one up. So just making up some numbers here. You can write this or not, but this will help explain what this function is and what it looks like. I am going to graph this one as well on the paper. If I plug in a 1, I get a 1. If I plug in a 1.5, I get a 1. If I plug in a 1.9, I get a 1. So notice what's happening. This is going to give me the greatest integer less than or equal to x. So round it down. What's the next integer equal to that or just below it? Like closest one to it. If I have 1.99, that's a 1. But as soon as I reach 2, I'm at 2. Or if I say 2.1, I get a 2. Or if I say, let's go crazy here, if I have a pi, well, that's 3.14, 159, and so on. That's a 3. Okay? If I say, now things get tricky. Let's dabble in negatives. If I say negative 0.1, you might be tempted to say 0. No, looking at the number line, well, there's 0 and there's negative 1. And negative 0.1 is right here, and I always have to go less. If it's not an integer, you go down. So this is going to be negative 1. So if I said negative 974.6, now getting really crazy, huh? Negative 974.6 takes it down to negative 975. Okay, the graph of this function, let me zoom in for you here a little bit. There we go. That's much better. It zoomed out from some other thing, and that's it. The graph of this function is going to look like this guy right here. Man, that is about the clearest coordinate plane I've ever drawn in my life. I'm reluctant to even write on it. I use that for graph paper. Okay, if I plugged in a 0, I'd get 0. If I plug anything between 0 and 1, but not including 1, I get a 0. So there it is. That does not look very clear, but it will be as you see the pattern. If I plug in a 1, I get a 1, and that works for anything up to but not equal to 2. And then if I plug in a 2, I get 2, and that works for everything up to but not equal to 3. This is called a step function, by the way, for obvious reasons. And if you're thinking this is impractical, think about postage rates. There's a graduated scale of how much it takes to mail something. So if it weighs between this amount and this amount, it's this much. If it weighs between this amount and this amount, it's this much. That sort of thing. Very practical stuff. Okay, that's what the function looks like. And now let's grab the official purple pen, and we're going to talk about continuity. And this one has a non-removable, and it's a jump. Now up over here, I called it jump and didn't say non-removable. That a jump is non-removable. Okay, you can say non-removable here too. Sorry to sidetrack, but I'm just throwing out some vocabulary. Non-removable jump discontinuity at every integer value. Okay, now we're going to answer the questions. Almost 9 minutes into this video, and we're going to finally answer the questions. Is f, that would be this one, continuous on the interval from -2 to 1, and if not, why not? Okay. Is f continuous from -2 to 1? All right. I have a discontinuity at -2, and that is okay because we do not include -2. Notice the parenthesis. But I do need to include a 1, but there is a hole in my graph at 1. So I have a discontinuity at the end of this interval. Now, we can get into the vocabulary of, is this interval closed or open? It is half open and half closed. I call it clopen or osed, depending on which end is which, but that is not official language. This one would be osed, open on one side, closed on the right. I don't see one that would be clopen. I didn't mix them up except on this problem where one half was open, one half was closed. But anyway, so answer on this, we'll use green. Is this one continuous on that interval? No. And we have a discontinuity at x equals 1. But we had to include 1, but it doesn't exist there. Okay? Is the function f continuous on the interval from -2 to 1? But this is an open interval. So I don't have to include -2, which is fine because we have a discontinuity. And I don't have to include 1, parenthesis, which is fine because we have a discontinuity. So yes, it is continuous. All right, fantastic. Is g continuous? Okay, look, I don't care what they ask about g. The answer is yes. This function is continuous everywhere. So 0 to 2, including 0 and 2. And just to be clear, from 0 to 2, but we have to cross over 1. If this function was broken at 1, like this one was, this is h right here, okay? This is h, but if this was g, if this graph corresponded to g, and they were asking, what happens from 0 to 2? Is it continuous? The answer would be no. It would totally be a no because we have not been continuous on every point in the interval. All right, so yes, it is. Is h continuous on the interval from 1 to 5? If not, why not? Oh, okay. Now things get fun. Now things get really, really fun. Okay, I want to go from 1 to 5. So let's just go ahead and talk about the obvious. It is okay to go beyond 1 and go all the way to 5 because the breaking point is at 1 for the h function. And again, here's the graph of h. This is truly the graph of h, and I want to know what happens if I am continuous going from 1 to 5. And this graph just goes way on up off the page. It's exponential. It gets crazy really quickly. So as we go from 1 to 5, we're good going past the 1. But what happens at 1? As I am approaching 1 from the right, the value of the limit is 2. The value of the function is 2. We're good. Okay? Let me talk about it in different terms. This is a closed interval. In order to have continuity on a closed interval, we have to have continuity on every point in the interval. Check. We have to be able to approach the left side and it match the value of the function. Check. We have to approach the right side from the left and it match the value of the function, which it does. We just can't see it because it goes up so high. So this one is a yes. Is h continuous on the interval from -1 to 1? If not, why not? Okay, well, let's do it this way. Same function, we're on h. This is number 5 on the notes. And I want to know if this function is continuous, closed interval, from -1 to 1. Now, this is supposed to be drawn like an open circle, although it doesn't look like it, so let's fix it to where it truly looks as open as it should be. Let's try this again. Make this look open, because that's going to, well, that didn't work. That just tore that white out all over the place. There, open circle. Trust me. Look, I'm going to fix this. I'm sorry to waste your time, but I'm going to fix it, and it's going to be so nice and so pretty. You're going to say, look at that nice little pretty graph. Man, look at that nice little pretty graph. That's a disaster. Okay, here's the deal. This is an open circle, all right? Trust me, it's an open circle. I got white out everywhere, messing up the desk. That's an open circle. But as I go from -1 to 1, I want to include the endpoints. So I'm cool over here. Like, this is fine. I can approach an x value of -1 and get an actual value that matches the value of the function. But as I approach this open circle that does not look open, there. As I approach this open circle, the value of the actual function is up here. So we have violated this requirement. As we are approaching the right end of the interval from the left, we get a limit that doesn't match the actual value of the function. So no, and I wrote that in purple. I meant to write it in green, but I'm not using the white out. I'll mess something else up. Let's just go with it. Keep writing in purple. Changing colors here. Is it continuous on the interval? If not, why not? Well, the reason why not is because the limit as x approaches 1 from the left of my function does not match the actual value of the function. One more time, when we talk about notation, you have to have f of x right here. You have to have something right here. You can't just say the limit as x approaches 1 from the left. As with what? What expression? What function? What are we dealing with? Is k, let's bump the camera, how about that? Let's get this ugly graph out of the way, how about that? Is k continuous on the interval from 0 to 1? If not, why not? So going from 0 to 1, and what we really have here is, let's pull that ugly graph back and use the back side of it. This is the graph from 0 to 1, okay, of the k function. As I go from 0 to 1, dealing with an open interval, I'm good. Like, I don't have to count the endpoints. I don't have an endpoint here, but I don't have to count it. I do here, but it doesn't matter. So, yes. Sticking with purple, apparently. All right. Is k continuous on the closed interval from 0 to 1? No. We're good over here, but over here, the value of the function does not match the value of the limit. So this is a no, and the limit as x approaches 1 from the left for my function does not equal the value of the function at 1. What I see coming in from the left is not the actual value of the function. Okay, and is m of x continuous on the interval from negative 2 pi to 2 pi? Of course it is, and here's why. Continuity cosine is just continuous, so that one would be a yes. There we go.